Hello, AP Calculus students. Today we are going to talk about a very important concept called continuity. We're going to talk about the definition of continuity, the types of continuity, and then we're also going to talk about something called the intermediate value theorem. I did want to update you that since we did have a day off on Monday unexpectedly, our test will still be the same day. What's going to happen, you were supposed to have a quiz next Monday. It'll bump to Tuesday. So we'll have a review day Monday, a quiz Tuesday. And I'll just make our test a 1-day test on Friday instead of a 2-day test. So when you're following your gold sheet, you'll be a day off, but then we'll catch back up because our test will only be 1 day. So today's assignment is actually coming from yesterday's date. So just make sure you're following the section numbers. So 1.4b is what you want to look at on the gold sheet for your assignment. So last night or this morning, whenever you finished it, you were supposed to go through that Desmos activity about continuity. So first of all, just pretty straightforward, a continuous curve is one with no holes or breaks in it. So you can see this curve is continuous because there are no holes or breaks. This curve is not continuous. Here, there is a hole, and so we have discontinuity there. And then here is a break. There is discontinuity there. Okay, so let's just talk about some functions that we know a lot about already. Okay, a polynomial is always going to be continuous everywhere. Okay, polynomials are smooth, continuous curves. Okay, there are no holes, there are no breaks. Polynomials are always continuous. So that's something that if you're ever given a polynomial, you shouldn't have to think too hard about whether it's continuous or not. We know they're all going to be. Okay. Now, if you're presented with a rational function, and we'll talk a lot about rational functions today, but rational functions are going to be continuous except where the denominator is 0. Okay. Rational functions can create either vertical asymptotes or holes where our denominator is 0, and both of those would be a type of discontinuity that we're going to talk about. Okay, an asymptote's going to cause a break, and then a hole is obviously a hole. So I wanted you to go through that Desmos activity so you could start to wrap your head around the concept of continuity and the stipulations that the definition has in order for a function to be continuous. So you kind of played around with some graphs and you had to write some things down. Since I'm making this video ahead of time, I can't really show you the answers that you're typing in because a lot of you haven't done it yet, which is fine, but I'm just having to make the video earlier than when you're doing this. So I'll look at them, well, by the time you're watching this video, I will have looked at your answers, but I can't show them to you right now. So here is the definition of continuity, and this is really important. You need to make sure that you write these 3 things down, okay? So number 1, f of c is defined, okay? And what we're talking about here is we're talking about a function is continuous at c. A function is continuous at c. So the first thing is the f of c is defined. This is just the coordinate, okay? does the function have a coordinate at whatever this x value is? All right, that's a terrible coordinate, isn't it? There, that looks better. Okay, next, the limit needs to exist. Okay, so you need to check that the left and the right hand limits are the same so that that limit will exist. And then the big kicker, and this is something that I sort of had you think about in your homework a couple times. The big kicker is that that function value and that limit needs to be the same. So the limit needs to be the same as that closed coordinate in order for these the curve to be continuous at that point. Okay. Now, I would not worry about writing down what's underneath about continuity on an interval. We'll kind of talk about some examples, and I'll show you how I would want you to notate that. So don't worry about writing this paragraph right here. The biggest thing is what I've highlighted in orange are what you need to be able to understand and remember, so that if I ever ask you to show me that something is continuous, you would use these things right here to explain it to me. Okay? So let's look at some things that are not continuous. So our number one, f of c, is defined. Here we have a curve that is not continuous because there is no coordinate at f of c. So here's our x value of c. And you can see that we have a limit that exists, but we have an open hole, which is fine for a limit, but it's not fine for continuity. Okay, so because of that open hole, there's not a function value there, then this is not continuous. Okay. Okay. Now the second stipulation is that the limit needs to exist at c. This one is a lot more obvious to pick out. Okay. Stipulation number 2, the limit needs to exist. Well, here is our x value c, and you can see that the limit from the right is different from the limit on the left, and so it causes a break. A break is a lot easier to see for us, and so this is not continuous. Because of that break. Since the limit doesn't exist at c, we don't have continuity. And then our third stipulation, this is the one we've talked a lot about it without knowing continuity, okay? We did some homework problems at the beginning of last week where I asked you about the limit and the function value. So here we have a limit that exists at c, and we have a function value at c. So I can tell you that each of those have a value, but since they are not the same, then this is not continuous. Okay, if we want continuity, this coordinate would need to be right here where their open circle is. But since it's not continuous. Yes, we have a value for the limit. Yes, we have a value for the function, but since they are not the same, we are not continuous. Okay. So I want to look at some graphs, and so we can decide where our functions are continuous. Okay, this is the graph of y equals sine of x. And we know from pre-calculus that this goes on forever and ever and ever and ever. There are no holes, there are no breaks. So we know that y equals the sine of x is continuous everywhere. Okay, the function is continuous everywhere. Okay. Now, this graph right here, the greatest integer function, we liked to sometimes call this the step function, okay? It is not a continuous function, okay? We have a break here, we have a break, here, here. Basically, at each integer x value, we have discontinuity. Now, I can say that from 0 to not including 1, we have continuity. And from 1 to not including 2, we have continuity. Okay. But the function as a whole would not be continuous. Okay. Now, I know that technically the function is not continuous at 1, but when I talk about the interval of this stair, we can have a bracket because it has it's at the end of an interval, and we have the right-hand limit and the coordinate, and so at the end of the interval, it's continuous, and then it would not be continuous at the right end of the interval. Okay, same thing here. This curve has no holes or breaks, but its domain is limited, okay? And I need you guys to get on board by remembering that this is a semicircle, okay? X squared plus y squared equals r squared is a circle. So if we have a number here, like 4, and we solve for y is plus or minus radical 4 minus x squared. Okay, so since it's the positive, it's the top semicircle, okay? With its limited domain, it is continuous. So we would say that we have continuity on the interval, the closed interval, -2 to 2, because we can include those endpoints since there are coordinates there, okay? So we've been talking about 2 types of discontinuity. Oh, not yet. Just kidding. Here's an example. And this is going to be something that's going to pop up quite a bit, problems like this. I want to know what value of A is going to make this continuous. All right? So we have a piecewise function. And it looks like we have a parabola and a line. Okay, so I'm just going to do a little sketching here. If we have part of a parabola and then part of a line, this would not be a continuous function. What would it need to look like in order for this to be continuous? Our line and our parabola are going to need to be able to meet up. So we're going to need to do that. Okay, so let's talk about the definition of continuity. Number 1, we need our function value to exist. So what part are we worried about in the domain? We have a break at 2. That's what we're concerned about for our limit and our function value. So we need to know that f of 2 exists. So since we have equality right here, then I'm going to plug 2 into this part. So our function value is 4a. Okay. Stipulation number 2, the limit needs to exist. So we need to look at the limit as x approaches 2 from the left and the limit as x approaches 2 from the right, and those are going to need to be the same. Okay. So 2 from the left is going to be this piece right here. So we're going to use direct substitution with this piece to get 4a. The limit from the right is going to be this piece right here. Okay. Well, now, in order for this to be continuous, we want our limit to exist, which means we want our right and left hand limit to be the same. So I'm going to take my left hand limit and set it equal to my right hand limit. Okay. So just to check our work, we need our function value and our limit to be the same. So if we plug a into our function value, we get 8/3. Okay? And if we look at our limit from the left would be 8/3. And our limit from the right would be 8/3. So A equals 2/3 is going to give us our continuity. Okay. Now let's talk about the types of discontinuity. I've talked about this a little bit already. We have removable and non-removable discontinuity. Hold off on writing this down because I'll go to two separate pieces where you can write them down individually. Okay, so I need you to be able to determine what type of discontinuity we have. Okay, and we're going to go back to kind of the break versus the whole. Okay, so the first kind of discontinuity we have is called removable. So removable discontinuity means the function can be rewritten in a way to make it continuous. Basically, removable discontinuity is going to be a whole without a break, okay? Like in this example here. Here we have discontinuity, and we could remove the discontinuity by filling in this hole right here, and then it wouldn't be discontinuous anymore, okay? So if there's a way to fix it by filling in a hole, then we have removable discontinuity. Okay, so basically if you have a rational function where you get a hole, okay, we are going to have removable discontinuity. Okay, now the kind that we can't fix, okay, the breaks that we can do nothing about, those are going to be called non-removable discontinuity. Okay, it cannot be rewritten as a continuous function, okay? This is where we're going to have our breaks, like asymptotes or the jumps. Okay, so we're going to go through some algebraic examples, and we're going to go through determining is it continuous or not, and what types of discontinuities are there if it's not continuous. Okay, so write down number 1, f of x equals the tangent of x. I know it's been a while since we did our pre-calculus, but I want you to remember that this is what a tangent graph looks like. Okay, sorry about that. I had a child who needed something. Okay, so obviously this is not continuous because of our asymptotes. Okay, so let me get this erased here. This is discontinuous. And they are non-removable discontinuities because we have asymptotes. And where are those asymptotes occurring? They're occurring at negative pi over 2, pi over 2, 3 pi over 2. So we're going to say that they're occurring at pi over 2n. Every, well, not so much. Pi over 2 plus pi n is where they're occurring. Negative pi over 2, 3 pi over 2, etc. Okay? Okay. Number 2. What kind of function is that? It's polynomial, which means it is continuous everywhere. Okay? Polynomials should be exciting in this unit, okay? Okay, here's a couple more. Number 3. Okay, number 3 should be suspicious because it is a rational function. Okay? Before we really get into it, let's go ahead and see if we can simplify. In the denominator, we can factor out an x. And you need to do this, okay? You need to do this with your rational functions, just like we do with limits. Okay, so the x's can cancel. So here's what we know. We have, we are discontinuous at 2 places. There are 2 places where our denominator is 0. One time at x equals 0 and one time at x equals 1. Now, since x equals 0 is where the hole is, this is considered a removable discontinuity because there's a hole. X equals 1 is our asymptote, so this is a non-removable discontinuity. You don't have to write asymptote and hole. I'm just trying to give you some things to look at, okay? Okay, and then number 4 is our last continuity example, and then we'll talk about the intermediate value theorem. So, if we have a piecewise function, what are we going to be nervous about in terms of continuity? We're going to be nervous about the break in the domain, okay? So first of all, stipulation number 1, our function value. Here's our equality. We're plugging 0 in here. Okay. Stipulation number 2, the limit exists. So we need to look at the limit as x approaches 0 from the left, and the limit as x approaches 0 from the right. Remember, I'm choosing 0 because that's where the break in our domain is. Okay. All right, so from the left, we have 4x plus 4. From the right, we have x squared minus 4x plus 4. Okay. Since f of 0 equals the limit as x approaches 0 of f of x, right? All of these are 4. Then this function, this piecewise function, is continuous everywhere. Okay, so last week and on your quiz yesterday, you've already gotten some practice at doing at least number 2, right? The limit of a piecewise function at that break. So now we're just throwing in the continuity piece to see if everything matches up. Is it continuous? Okay. All right, so you're going to have some homework problems about continuity and what types of continuity, both graphically and analytically like this. Okay. The next thing we're going to talk about very briefly is something called the intermediate value theorem. So I want us to think about this real quick. All right, so my husband and I measure our children every 6 months, birthday and half birthday. Okay, my youngest measured 44 inches and then 46 inches. He was upset that he never measured 45 inches. And he's about to turn 6, and this was, I think it might have been around his half birthday. Okay, so he was 5.5. What is wrong with his logic? He should not have been upset, but he was. He really wanted to be 45 inches. Turn to a neighbor and explain your thought process of why Riker-Hohmann had some delusional logic here. Okay. Riker's my child with red glasses, so we'll make sure we get that in. Okay. So I hope you turned and talked to your neighbor that we grow continuously. So while, yes, he measured 44 inches and then he measured 46 inches, at a moment where we didn't measure him, he at one point was 45 inches. Because we grow, did you hear that word? Continuously. We grow continuously. So we're going to apply that to functions, okay? As long as we have a continuous function, okay? And I'll let you write this down first before I show you a picture. So if a function is continuous between a and b, then it takes on every value between f of a, that's a y value, and f of b, that's a y value. Okay, so as long as there are no holes or breaks in our graph, as long as we're continuous, then whatever our y value is at A and whatever our y value is at B, then any y value in between is going to have a coordinate on our graph somewhere. Okay, so let me put some numbers here to help you out. If this is the coordinate a, 1, and this is the coordinate b, 5, then there's going to be a coordinate somewhere with a y value of 2, with a y value of 3, with a y value of 4, with a y value of 2.5, with a y value of 4.9. All of those numbers in between 1 and 5, there is going to be a coordinate, or 2 or 3 or 4, but at least one coordinate somewhere between A and B. Okay, so kind of like Riker growing, right? From y value to y value, as long as we're continuous, we're going to hit those numbers in between. Okay, how could this be of benefit to us? Okay, the intermediate value theorem is actually something that's going to jump out throughout the course of this class, and especially when we prepare for the AP test, it'll be something that will really come in handy. But let's talk about just a couple simple examples. So you're going to have some homework problems like this. Prove that f of x has a 0 on this interval. So I'll go ahead and let you write down the interval, write down the function. Okay, so the intermediate value theorem deals with y values. So let's figure out the y value at -2 and the y value at 1. So just go ahead and plug in -2 to this and then plug in -1. Excuse me, +1. Okay, we're going to need to do something here. Let's go ahead and change this to x cubed. Sorry about that, guys. Let's change that to x cubed. If we plug -2 in, we would get -8 minus 8 plus 3 for -13. And if we plug in 1, we get 1 minus 2 plus 3, which is a +2. Okay, we want to prove that there is a 0. Okay, well, 0 means our function value is 0. Okay, first of all, we have a polynomial. We know this is continuous. So, since f is continuous, and 0 is in between -13 and 2, then there exists a 0 on the interval -2 to 1. Okay, so we have y coordinates on opposite sides of the x-axis, and since we're continuous, the intermediate value theorem tells us we're going to have to hit 0 at some point on that interval. So this is what I've explained right here. Since 0 is a y value in between our two y values, then it's going to happen on our interval. Okay. All right, we have one more intermediate value theorem example. It's going to look a little bit different. Okay, this time I'm giving you a function and an interval, and I want you to show that the y value of 10 is going to happen. So go ahead and write it down and we'll go through it. Okay, so our intermediate value theorem first deals with continuity, and we know that we are talking about a polynomial, so this is continuous. And then we also care about the y values. So let's take these two and find our y values. All right, 0 is easy to plug in, right? We have 4. When we plug in 5, we're going to get 25 minus 5 plus 4. Okay, so it's going to take more time to write out what our brain is thinking right now. Okay, so let's just talk about our thought process. 10 is definitely in between 4 and 24. So we know that this is going to happen. Okay, so since f is continuous, and we know that 10 is in between 4 and 24, then we know there is an x value in our interval where f of c equals 10. So let me just explain this one more time. 10 is in between our two function values, so that c is in our x interval, f of c equals 10. Okay, a reminder, I have office hours tonight from 7:30 to 8, so if you have any questions about something that happened on your quiz or something from this lesson and your homework, please pop on. If those office hours don't work, email me. We can work something out either via email or something else. And then look for your quiz feedback via email at some point. I'm not sure if it's going to be today or tomorrow. I'm grading them. I just have to make sure that I have